Bismillahirrahmanirrahim. Assalamu alaikum. Now we are talking about part B of the unit 6, which is the models and similitude. What is the models and similitude? We will learn in this unit, and we will see how to apply this information and this analysis of the models and similitude. So, models and similitude, this is a study generally we do when we study a big structure. For example, if we are talking about hydraulic structure yani related to the water, because we are talking about the fluid, so like the dam, like a spillway, and any big river or the channel. So when we are studying on this big hydraulic structure, instead of going for the real object, we make a small model of that, and we study the property of that big channel on this small model. And once we find out this is a good design, safe design, economical design, then we build the actual structure. For example, if I want to design a dam, water dam, big dam, so what I will do, I will make a small model of the dam. Then I will study the velocity, the flow rate, and the hydraulic property, gradient, slope, everything. Then once I see my design is economical and safe structure, so then I will go for the actual design. So this study actually help us to make a small scale model to predict the behavior. Predict mean to get the idea, to uh, guess that what will happen in the actual structure. So this is the study which is called as the model and similitude. In the model study, generally we use the basic theory of the hydraulic similitude, and we will see how we can apply this information in the coming slides. And this theory of the hydraulic similitude actually involves the study of the similarity of the hydraulic structures, their relationship, for example, the shape of the structure, and the weight of the structure, the other property, density of the structure. So we study the similarity in the two things. One is called the model, and actual one is called as the prototype. So we study the prototype and the model to understand the properties of different hydraulic condition. All significant hydraulic structures are generally designed these days after doing a basic study uh, on the models. Once we complete that study, then we go for the actual designing. So this is the model and similitude study. This study is applied to many areas. There are several areas where we can apply. For example, these are some of the list of the different purposes where we can apply the model and similitude studies. For example, to determine the discharge coefficient in a large measurement structure like a overflow spillway on a dam or a weir. So we determine the discharge coefficient in the lab by doing a model study. Similarly, we can develop effective method for energy dissipation or energy release in the outlet of a hydraulic structure. For example, at outlet of a dam, how much energy will be released when the water will fall from a certain height. So this we can study in the model also. And also we can study to reduce the energy losses in any structure like a pipeline or any canal. We can study in the model. And also to develop an efficient economical spillway or any other type of the flood releasing structure, or for reservoir, for a tank, for a dam, anything, we can design a effective, efficient structure, and it should be a economical structure. Also to determine the average time of travel in a temperature control structure. For example, in a power plant, when the water goes inside the power plant to cool the heat, transfer the heat from one point to another point, that study can be done on the model also. And also to design a best cross section, economical cross section of any hydraulic structure, we can apply this model similitude study. Also, in order to determine the dynamic behavior, dynamic mean when the water is flowing, the fluid is flowing, then what is the floating characteristics, immersible characteristics, and what will happen to the bottom of the structure when there is a shape or any carrier. So that study we can do by doing the using the models instead of directly going to the prototype. Also to determine the pattern of the flood waves. For example, we are studying the when the flood is coming at the edge of a seaside, what will happen, or in a river. So that study we can do in the models also to determine the effect of artificial structures such as the band, levees, any water structure, jetties, training walls, sedimentation movement in the channel, all we can do in the model instead of doing in the actual structure. Also to determine the direction and force of the natural and anthropogenic currents, yani human made activities in the channel. For example, a boat is moving in the river, or the ship is moving in a canal. So these things are we study in the marine structures to determine the different type of the forces and the movement of the waves. Many things we can do by model studies. And when we do the model study, we use the dimensions. And you remember from the part A, the dimension for various quantities like the length, area, volume, discharge, velocity, all these are known to us. So we can use this dimension to find out the similarities between the model and the prototype. When we do the study on the models to study the behavior of the prototype, we can classify our study into three classes to simplify the understanding. So it could be a geometric similarity, it could be a kinematic similarity, it could be a dynamic similarity. And in a specific problem, we find out in which class this problem is lying. In the geometric similarity, yani shape is similar. Kinematic similarity, when there is a the dynamic velocity and the dynamic conditions are similar, movement of the fluid, for example. And in the dynamic similarity, like the force is acting on a dam or any structure is similar, then we apply this kind of the similarity. We will see one by one each of them. The geometric similarity, for example, geometric similarity is the similarity of form. Like for example, we have a shape, rectangular one, for the prototype actual one. Then when we make the model, it should be having the same ratio. For example, this length is 10 and this is 5, half of that. So then if it will be 4, it should be 2. So the ratio of these sides should be same. So this is called the similarity of the form. So geometric similarity achieved by maintaining a fixed ratio for all corresponding length between the model and prototype. So the ratio of the length and the width and the height should be same. So we can say that length is saying by L, the area which is actually the A, which is can be expressed as L square. Volume can be expressed as L cube. So the ratio of the prototype on model should be constant. I'll say the length ratio should be LP over LM, right? Area ratio should be AP over AM. Volume ratio should be prototype over model LR cube. So this ratio between the dimension should be same in case of the geometric similarity. Let us see the application of the geometric similarity in a by a problem. A question saying that a geometrically similar open channel model is constructed with a 5:1 scale. So this is the ratio of their length, yani LR. For example, if the length of the prototype is 5, then the length of the model is 1. If the width of the prototype is 5, then the width of the model is 1. So this ratio existing in all the dimensions. So this is LR. It is given. If the model measures a discharge of 7.07 cubic feet per second, this is the Q for the model, right? What is the corresponding discharge in the prototype? I have to find out the Q for the prototype. So this is the data. Let us see how we can solve this problem. I have uploaded this one also. So you can see that in the question it is given that the ratio LR is 5:1. 5:1 mean 5 over 1, and LR mean LP over LM. So this is 5. This is given to us, and the Q for the model is given to us 7.07 cubic feet per second. We have to calculate the Q of the prototype. Now let us start with the continuity equation, because in the continuity equation we have the Q which we can calculate in this question. So if I will write this formula for the ratio, for the ratio of the prototype and the model, I can write same formula as QR equals to AR into VR, right? This formula in the same way. And we know that the QR is QP over QM. like LR is LP over LM. Remember always the ratio is the prototype over model, right? So the QR will be QP over QM. Similarly, AR will be, you can say that area is length square, so it is L square, and velocity is the length over time. So you can write that the LR cube over this is the LM cube, right? So when we have that, right, LR is actually the LP over LM, which is in the cube, because LR1 and LR2 is making the cube, and this is 1 over TR. Now this is actually LR cube. What is LR? This is 5. LP over LM or LR is this one. So I can write this LR cube, right? So once I will write this here, uh, LP over LM, right? And this is LR over 1 over TR. Then this is LR cube and this is TR. And once I cross multiply, QM will go here, and QM we know that 7.07, LR we know that is 5, and TR is 1. Remember, in the dimensional or geometric similarity, that there is time ratio is same. There is no time ratio existing, yani the time for prototype and model is same. So in this case always TR equals to 1. So then we can simplify the, we get the Q for the prototype in cubic feet per second. So this is the application of the information to calculate the discharge from the prototype, and we know the discharge of the model. So this is the application for the geometric similarity. Similarly, what is the kinematic similarity? Kinematic similarity is due to the motion, kinetic energy. So it says that the kinematic similarity is between the model and the prototype when it is having the homologous moving particles with the same velocity ratio along the geometrically similar paths. So if those yani model and prototype having the similar movement, like the velocity of the fluid in the model is same the velocity in the prototype, then the kinematic similarity is existing. So here you will find always there is a time ratio and there is a length ratio. In the previous one we were having only the length ratio. So in this case we can say that time ratio is TP over TM. Ratio is always P over M. So we can apply this information and we can develop the other information, the velocity also, because velocity I know that it is L over T. So LP over TP, V for M is LM over TM. If I simplify rearranging the L together and T together, it will become the LR, it will become the TR. So LR over TR, and this is actually what VR. So VR equals to LR over TR. Similarly, for the acceleration, we can develop the AR equals to LR over TR square, because we know that the acceleration is length over time square. Similarly, for the Q is actually the volume over time. So the LR cube over TR. So in this way, we can have formulas for various quantities, and that can be utilized to solve the problems related to uh, the application of this kinematic similarity, and we can use the time scale and the length scale ratio. Let us see from the one of the problem how to apply this one. For example, in this case you see that 10:1 scale model is constructed. So this LR is given to us, the length ratio is given to us. So studies is going on to the flow movement in a cooling pond. The design discharge from the power plant is 200 cubic meter per second. So this is the actual flow from the power plant. So it means that it's QP prototype. The model can accommodate a maximum flow rate of 0.1 cubic meter per second. So this is the QM from the model, the Q from the model. So the Q from the prototype and Q from the model is given. What it is asking? Calculating the time ratio. So we have to find out the TR, right? So this is the question. Let us see how we can apply this in this question. So this is the question. You know that in the question LR is given to us 10:1, yani LR is 1. Q for the prototype is given to us, Q for the model is given to us, we need the TR ratio. Now we know continuity equation, right? And the QR is the QP over QM, right? And this is given to us 200 over 0.1, right? AR is actually LR square, and VR is LR over TR. So I can write this LR cube over TR, this quantity, right? LR I know 10, right? And TR I have to calculate. So once I simplify this, I will get the TR. So this is the application of the kinematic similarity, right? Similarly, in the dynamic similarity, here we are talking about the forces. We are looking for the different type of the forces on the prototype and the model, and these forces are having the fixed ratio on the prototype and the model. So the dynamic similarity between a model and the prototype is attained if the ratio of the homologous forces is kept at a constant value. Yani there is a force ratio always, right? The force ratio is applicable in the dynamic similarity. And if you use this information, you can come up with the various formula. For example, for FR is FP over FM, and you know that the force equals to mass into acceleration, so MP over AP, and this mass is actually density into volume. The density having the unit of the kilogram per meter cube, and volume having the meter cube. So this is actually the mass, right? And this is the acceleration. If you further simplify area acceleration, you can write the L over T square, right? Here we are talking about the P, so all are P here, right? So this we get at the top. Same thing we do with the M, so we will get the same thing at the bottom. This rho P over rho M is the rho R, the ratio of the density. Generally, for making the model, we use the same material. So the material is same for the model and the prototype. And that rho R will be 1 always. So because this both values are same, so generally in the question you will find that rho R is 1 until unless it is given. LP, here you can LP cube, here LP, so it will become LP 4. So you can see the LP 4 over LM 4 also there, so you can write LR 4. Similarly, the TP over TM is the TR, so it can be write as TR square per unit. That's one. So the force ratio is this formula. You have to remember this formula. So the force ratio equals to rho r LR square TR minus 2 times, yani 1 over TR. Similarly, you can apply to this formula for the mass ratio. You will get this formula FRTR square over LR and then work ratio also. You can calculate the work ratio WR, which is force into distance, FR and the power ratio, yani PR equals to force multiplied by the length divided by the time. So FR over TR. So these 1, 2, 3, 4 formula you have to remember that can be applied in the dynamic similarity. Let us see how to apply in the numerical. The question saying that 59,700 watts pump. So the power of the prototype pump is given to us. Yeah, this is actual pump. So this is the P is given to us, power of the pump prototype is used to power a water supply system. The model of the same material. So same material mean the rho R is 1. It is constructed to study the system which has a 8:1 scale ratio. So this is LR is given to us. Now the velocity ratio is also given to us. The 2:1, so the VR is given to us. What is the power needed for the model pumps? So it means that the power for the prototype is given to us. We need to calculate the power for the model, right? So how we can apply this one? Let us see the solution for that one. In this case, you can see that the the power of the prototype is given to us. The length ratio is given to us 8:1, 8, yani velocity ratio also given to us 2:1, yani 2, and we need the power of the model. The formula of the power which we see in the previous slide when we were talking about the similarity. Okay, so you can see that is FR LR over TR. This is a power ratio because we have to solve for the power, so we can use this formula. So this FR LR over TR. Now we know that this Fr is the mass into acceleration. You can further simplify this one also. If you will simplify this one, what you will get that the mass into velocity, this is the same thing which we have done in the previous slide, and the acceleration length over time square, right? So rho r will become 1, the volume is lr cube, and lr is here from here, and tr square, this will become tr4 lr4 and over tr square. This is fr. We can put this value instead of fr here. So once you put this one here, right, so this formula will become like this one. Now after simplifying, lr4 and lr will become lr5 and tr square, right? This is pr. Now also we have the velocity ratio. Velocity is length over time, so the vr can be lr over tr, right? We have to calculate the pm, so for that we need the tr. So from this formula, from the velocity, we can find out the tr, because the lr over vr equals to tr. So lr we already have 8, vr already we have 2, right? From here, right, we can find out the tr. Now we have the tr, right, and we have this formula. We can put this here, and we can use the pr equals to p over pm, pp over pm, and lr we have the 8 and tr we have the 4. Once you will put here, then after simplification you will get this one. So pp over pm equals to 512. We need the pm, so pm will be equals to pp over 512. So this pp we already have, power of the pump. Then after simplification we get the power of the model, 116.6 watts, right? So this is the application of this dynamic similarity, and these similarities help us to design an actual system, hydraulic any structure like the dam or the river or anything. And after doing this study, we can come up what should be the actual dimension and the properties of the real structure. So this is all about the dynamic similarities and model and similitudes. If you have any question, anything which you want to discuss with me, kindly let me know. We can discuss this again. So please go over these problems and the notes. Inshallah, it will be helpful for you. Thank you very much.